in the first lecture about some of the key concepts or some of the general terms that you need to appreciate and understand regarding pharmacology. And we covered essentially permeability of the cell membrane. We covered pKa value and what does it mean actually to the permeation of the drugs into various tissues, and the factors that can affect actually the distribution of drugs. So this type of information being shared with you before, and today we like to focus on the two aspects now, pharmacodynamics and pharmacokinetics. Okay. The pharmacokinetics, we're going to go over it a little bit fast, but there is a need for that, is to emphasize on P450 again, and to emphasize on the terms and the equations that you need to master in this section, and also to familiarize yourself with the plots that are addressed. And then we'll move on to pharmacodynamics, essentially. And that is, we like to see the drug-receptor interactions. We like to address efficacy of a drug, affinity of a drug toward a specific receptor, and equally significant, we like to address what is meant by the therapeutic index, what is meant by the broad spectrum versus the narrow spectrum, and how is that ties with drug-drug interactions. So that's very important to appreciate, and to be able to address in some detail agonists, antagonists, partial agonists, and see how drugs actually act as an agonist or as an antagonist. So that actually will smooth the way to you actually to understand adrenergic drugs, cholinergic drugs, because when we move on to those classes, we will address in detail agonists and antagonists for each class. So you have to be very well familiar with those terms and the side effects and all of that. I meant, actually, I was reluctant between adding the information about molecular signaling mechanisms, and it is very important to address that actually before you started the general classes of pharmacology, like cholinergic drugs or adrenergic drugs, PNS, CNS, and all of these classes. The reason for that is I like to use this as a smooth transition to address receptor specificity and subreceptor specificity. Okay, and the only way you really can address this is by addressing molecular signaling. So I'm going to leave that for the next lecture, and let's focus today on essentially the basics of drug distributions, the basics of pharmacokinetics and pharmacodynamics. So that's the objective for today's presentation, actually. With that said, let's start out the lecture. I was moving actually the slides in the wrong direction, so please accept my apology for that. Okay. With pharmacokinetic aspects here, so we like to understand actually distribution of drugs. We like to address bioavailability of a drug. We like to address essentially clearance of the drug, okay? And we like to address all of those terms in a nice fashion and in a fast fashion in order to understand these basic concepts. So I'm going to go over this fast. So what you see in here figure is a presentation about the bioavailability of a drug. So essentially, if you inject a drug intravenously, so you expect its bioavailability to be 100%, and that's what you see here, area under the curve. Okay, versus if you inject, or if you give a drug orally, so you're actually dealing with the first pass mechanism, and the area under the curve will be much less, actually, when you compare it with the area under the curve for injected drug. Okay, and you can relate this type of relationship. So the ratio of the area under the curve when a drug is given orally over the area under the curve when a drug is given intravenously. So this actually will give you the bioavailability of a drug. With that said, we have to address the factors that can affect this drug distribution, essentially. So you can see that the rate of perfusion is a major factor. Plasma proteins, of course, drugs tend to bind with protein, so the extent of their affinity toward protein will count in terms of the drug distribution. In terms of drug-drug interactions, of course, you expect to see an effect on that. So if you have a drug that tends to kick out this bound drug from plasma protein, so you can see the pronounced effect on that, and also the pronounced side effect. So that's important to appreciate. Accumulation of the drug in different tissues, that's also an important factor to consider. And of course, the most important aspect of it is the ability to cross the membranes. So here we're dealing with the blood-brain barrier that actually has a decent screen. Allow only, as I said before, allow only those fat-soluble drugs to pass through, right? And prevent the other ones. So you're facing this problem in terms of distribution. With few drugs, they have specific transporters. And placental barrier also can be a factor. Okay. So I listed this parameter to you here in a nice fashion. So the transport of a drug into the body by bloodstream to its site of action depends on its protein binding, water-soluble versus fat-soluble, blood-brain barrier areas of rapid distribution, essentially heart, liver, kidney, brain, okay? But when you deal with the adipose tissue and you deal with the muscle, so you expect to see it slow. So you can see that area of slow distribution, muscle, skin, and fat deposited material. There is, of course, we already addressed what's meant by the bioavailability here, the rate at which a drug leaves its site of administration and the extent to which the drug is absorbed. So that's a bioavailability, and you can measure that by the area under the curve when a drug is given orally over the area under the curve when the drug is given intravenously. Okay. Now, in terms of bioavailability and bioequivalence, okay, so essentially we're talking here about two drugs that they considered bioequivalent, so their distribution is the same, and therefore you do not foresee any problem. So you can use this term to address both. Bioavailability is the same as bioequivalence in here. Okay. Let's see what we have. Yeah. This plot here shows actually the assuming that there is no clearance of the drug. So, so you're giving a drug intravenously, and you follow the distribution phase. And you can see that what you're dealing with is a first order kinetics here. And the reason that you see this plateau stage is the fact that we're not considering the clearance of the drug in this plot. That's after single injection. Versus if you consider the elimination phase here, so you can see also that this follows first order kinetics. So that's a drug distribution versus a drug elimination. So you have two phases here, distribution phase versus elimination phase. There are some specific equations here you have to deal with, and that deals actually with the concentration of the drug, okay, dose of the drug giving, and the volume of distribution. So this is, and you can manipulate this equation any way you wish to in order to determine either the concentration you need to achieve and make adjustment for the dose, so you can use this type of equation, or vice versa. You can evaluate the volume of distribution if you know the dose that you are given and the concentration that you want to achieve. So that's a total amount of drug in blood versus the plasma concentration of the drug. And all of those equations are very important to appreciate and to focus on. What you see here in this curve and in this plot, and that can be subject to questions actually in USMLE exams and in standard exams. So you can be given a plot like this, and you are asked to evaluate the concentration of the drug at C0, okay, or to determine the half-life of a drug and things like that. And all of the information are listed to you here in a nice fashion. You cannot really ask for more than that. So what you see here is essentially the serum concentration of the drug versus the time. Okay, and what we stated about the T half is the amount of time which is required for the drug to be eliminated, half of it to be eliminated within this section of time, or within this time interval. So that's important to appreciate. And simply, you can see again that the kinetics of the distribution follow a first order kinetics here, and also the kinetic of the elimination follow also a first order kinetics. So we see that in this fashion. But the most important thing here out of this is how you determine actually the concentration at C0. And the way to do that is to try to extrapolate, to try to extend this decent straight line until it intersects with the y-axis. And your reading here will be C0 here. So that's so it can be extrapolated back to time 0, and that's a time of injection to determine C0, which in essence is the concentration of the drug that would have been achieved if the distribution phase had occurred instantly. Okay. For example, let me give you an example. If you give, for instance, 10 milligram of the drug, and those are injected to the patient, and the plasma concentration, you try to extend it all the way up here, so you end up with C0 is 1. Okay. So all what's left really, you know the drug that you give it, and C0 is given to you here. You can extrapolate it, so you can easily determine the volume of distribution, right, from the previous type of reaction. So you know those two, so you can determine the volume of distribution. And the volume of distribution here will be 10 liters. So this type of manipulation, you should be able to get it, and determination of the T-half. So there is a lot to learn actually by looking at this plot, and lots of valuable information you can get when you look at this plot. And please keep in mind that the volume of distribution is very useful. Why is that? Because you can actually calculate the amount of drug which is needed to achieve this desired plasma concentration. Okay, so let me give you an example for that. Okay, so if you are dealing with arrhythmias of cardiac patient, okay, and you found out that it's not well controlled due to inadequate plasma levels of digitals, for instance. So assuming that the concentration of the drug in the plasma is C1, let's assume that here, and the desired level of digitals, okay, which is known actually from the clinical studies that you are aware of it, is at much higher concentration level. Let's assume C2, for instance. So what the clinician do is essentially, or what he needs to know, is how much additional drug should be administered to bring this circulating level of the drug from C1 to C2. That's in a simple terminology. Okay, so how are you going to achieve that? So you have the volume of distribution times C1. That gives you essentially the amount of drug initially in the body. Okay, and then you can evaluate C2, okay, and then you say the volume of distribution times C2, and that's the amount of the drug in the body which is needed to achieve the desired plasma concentration. So if you take the difference between those two values, so what you're going to get? So the difference will be volume of distribution times the new concentration that you want to achieve, that's C2 minus C1. Simple and easy, and that's what you're going to deal with as a clinician. And that's what they're interested to know, actually, in a standard exam. Are you aware of this terminology? Are you aware of those terms? Can you make a logical sense out of it? So it can be addressed in a clinical scenario like that. Digital is a very good example to see that. Good, good, good. And please appreciate the fact that when you have a high volume of distribution, so this is very important. It has very important influence on the half-life of the drug, okay, because what you're dealing with is the elimination will depend on the drug that is delivered to the liver or the kidney. So you have to pay that to give that your best judgment and your best thoughts. And also, please also consider that the delivery of the drug to those organs of elimination will depend not only on the blood flow, but also on the fraction of the drug in the plasma. Okay. So the blood flow will count a part of it, and also the plasma concentration of the drug actually will count another part. So let's assume that the volume of distribution is high. So what that says that most of the drug is in the extraplasmic space and is not available to the excretory organs, not available to be excreted. So those terminology you have really to understand it to a great extent. And any factor that increases the volume of distribution can, in fact, increase the half-life and can extend the duration of action of this drug. Okay, so this is all great information that I shared with you, and I hope you take it in your serious consideration. Let's shift the gears and address binding of drugs to plasma protein. So what you see here is binding, actually, binding capacity of albumin. So you have to take in consideration that bound drugs are pharmacologically inactive, just like the same way as bound proteins, they are as bound hormones. So they are also inactive. You only deal with the free form. So only the free unbound drug that can act on the target sites in the tissues. So that's important to appreciate. What you see here in the first figure here, A, what you see actually that the binding of those drugs to albumin is reversible and may show low capacity. So you have one drug molecule bind to albumin molecule. Or you're dealing actually with a high capacity number of drug molecules binding to a single binding molecule. So you deal with low capacity, high capacity. So those drugs that can bind with varying affinities, okay, essentially that's what you expect to see. So what you're going to see actually is the beauty about serum albumin, that it has the strongest affinities for anionic drugs. It has a strongest affinity toward weak acids. We said drugs function as weak acids or weak bases. So you have to keep that in mind. And also hydrophobic drugs. So this is the class that you expect to see high affinity towards serum albumin. But in terms of hydrophilic drugs or neutral drugs, they don't bind effectively with albumin. So that's a very basic concept. We have to appreciate it and understand it. The second aspect here that you're dealing with in figure B here, you have to appreciate the competition for binding between drugs. So when two drugs are given together, so one with a high affinity for albumin, so they compete for those limited available binding sites. You see here, you're dealing here with nice competition. And the same applies actually for drug receptor interactions, as we're going to address agonists, partial agonists, antagonists, and you're going to have lots of fun on that. So the drugs with high affinity of albumin, actually you can subdivide that into two classes. It depends on what either of the dose of the drug or the amount of drug found in the body is under conditions used clinically is greater or less than the binding capacity of albumin. You see that? So you're actually comparing apple with apple here. You have binding sites and you have the drug. Is it below the capacity or above the capacity? That's what you're dealing with. So the capacity of serum albumin, normally you can quantify that as a number of millimoles of albumin multiplied by the number of binding sites. So that's an easy concept to appreciate and to accept. So what you're dealing with is two classes of drugs. The first drug is if the dose is less than the binding capacity. So you expect to see that the dose to capacity ratio is low and you got what you need. The drug is bound nicely to those serum albumin, assuming that it meets the specific properties. What are they? Anionic, weak acids, and hydrophobic. So that's what you should keep in mind. Okay. So you will see actually that the binding sites are in excess of the available drug, and the bound drug fraction is high. And this is the case for majority of the clinically useful drugs. With class 2, you will see actually that it's other way around. Those drugs are getting in doses way exceed the number of albumin binding sites, and the dose to capacity ratio is high. And therefore, what you expect to see here is high proportion of the drug do exist in the free state. So that's one thing you have to consider it in mind. The most crucial thing in terms of drug displacement reactions and drug-drug interactions is to accept the significance of this classes when you address with warfarin, for instance. So when a patient is taking class 1 drugs such as warfarin, which actually belong to class 1, binds with a great affinity, and then you prescribe to this patient a drug which belongs to class 2 here, like sulfonamide, for instance, antibiotic. So what's going to happen here is that warfarin binds with a high affinity to albumin, and only small fraction is expected to be free in circulation, okay? And when you give this patient sulfonamide, so you're actually kicking this bound form of warfarin into circulation, and that can lead to tremendous increased therapeutic effects. And also you have to consider tremendous increase of risk factor, toxic effects. And in the case of warfarin, you expect bleeding. So this all have a decent application that I like to share it with you, and it's all beautifully illustrated to you here. Good, good, good. So we address that, and you see this type of displacement that I talked about it here nicely. So I like you to place that on your hard drive, essentially. Another point of interest related to this material, you have to address actually the relationship of the drug displacement to volume of distribution. We already mentioned. You understand mechanistically what happened when you displace a drug with another drug, but what's the effect of that on the volume of distribution of that drug? So what you should keep in mind that the impact of drug displacement from albumin, it will depend exclusively on two factors here. Volume of distribution does not move into the tissues, right, as much. And therefore, you expect to see a tremendous increase in free drug in plasma, which is more profound here. And when you consider the therapeutic effect, therapeutic index, if the therapeutic index of the drug is small, so this increase in drug concentration may have significant clinical consequences. And that's the important thing that you have to appreciate in terms of drug-drug interactions. Good, good, good. Okay. Let's shift the gears to drug metabolism and pharmacodynamics, and this beautiful illustration here in terms of pharmacokinetics aspects. When you look at this plot, that actually simply represent the effect of dose on the rate of metabolism. And this is very similar to what you used to see when you covered biochemistry in terms of enzyme-substrate interactions. It's a hyperbolic plot that shows actually the rate of the drug metabolism follow a first-order kinetic at low concentration, and then you're achieving a plateau stage. That means you achieved a saturation level. So, and you can deal with it exactly as Michaelis mentioned. So, initial velocity equal to Vmax over C concentration times C concentration over Km velocity concentration of the drug. And you can, based on that, if you manipulate the equation, you can very much, I'm not going to go over the equations and stuff like that, you can look it up. But essentially, if you manipulate the equation, what you're going to see is that the rate of drug metabolism will equal to the maximum rate, that's expressed as Vmax, for instance, times the concentration of the drug over the affinity of the drug toward a specific receptor or a specific binding site, which is represented as Km. You have to consider the fact that majority of the drugs actually follow a first-order kinetics, and this is important to appreciate it. Only few drugs that follow actually a zero-order kinetics, like aspirin and ethanol and phenytoin. So those doses, when it's given very large, so you achieve this saturation level, and it follows a zero-order reaction. When we talk about reactions of drug metabolism, you have to consider phase 1 and phase 2. So phase 1 here function to convert actually those lipophilic molecules into more hydrophilic molecules. Okay, so you try to play around a little bit with the structure of the drug, and you can do that by unmasking polar functional groups, for instance. And of course, the you expect to see out of the phase 1 metabolism, it can decrease, increase, or leave the site unchanged. Okay, with phase 2, so you're dealing here with conjugation reactions. So you're dealing with, and this is nicely illustrated to you in this figure here. So you see the drug, certain drugs actually when it's giving intravenously, so you're bypassing phase 1 and you're jumping into phase 2. What in phase 2 here you are dealing with? You're dealing with conjugation products. So some of the drug directly enter phase 2 and you're dealing with conjugation. So conjugation of the drug will essentially tend to convert this drug to be inactive. Phase 1 here you're dealing with the drug can be activated, unchanged, or most are inactivated. So an appreciation about that is needed when you deal with it. Those are the various effects that you expect to see. Transformation of drugs to a less or more it depends more polar when you excrete it, and more hydrophobic if you want to reabsorb it. Alteration of solubility is a very important factor to be considered with the biotransformation. The liver is a factory of everything. You have all the machinery equipment that you need. You have P450 involved. You have the glutathione is very rich there, so you have to consider that, and therefore any problems with the liver, you will tend to slow down the metabolism and to prolong the effects, of course. P450, you cannot leave home without it. You cannot leave home without P450 complex. It's made up of 5 isozymes. Each one has a specific specificity toward particular substrates. Each one can induced or inhibited by function of various drugs. So this is what you're going to deal with in terms of drug-drug interactions. What type of reactions does it follow? You're dealing with all of those reactions: aromatic aliphatic hydroxylation, dealkylation, oxidation, sulfooxidation, hydroxylation, deamination reactions. All of those you deal with them nicely with the P450. And I listed to you here a couple of tables that I want you to sleep on them. I want you to go back and forth when you address each class and says, well, okay, now when I click, I says, well, okay, drug-drug interactions plays a part. So I can say, well, that's what you expect to see with this class of drugs, but I can say, well, okay, go back and look at those tables. It have everything. It's a Bible of everything. See that? So you can see actually the common substrates here for each isozyme. Okay, so you have warfarin, phenytoin, ibuprofen, tolbutamide, and the ones that act as an inducers, you see. So if you have a patient, for instance, had warfarin before and you give him phenobarbital, so what do you expect to see? You see phenobarbital will induce this, right? So when we say will induce, so it will essentially enhances the metabolism of those ones versus inhibitor the metabolism of those ones. So you can relate that to the volume of distribution. You can relate that to the free available drug. You can relate that to the toxic effects. That's a trend of thoughts. That's what you should have in mind. The same classes. So with each isozyme, you're dealing with different classes of substrates, and you see that nicely addressed here. So inducer. So you already got your share with that. When you look at the elimination, so as I said, kidney is the primary site, and therefore any problems with the kidney, of course, will affect the excretion of the drug in terms of prolonged effects, slows excretion. So those mechanisms will depend on passive glomerular filtration, GFR, okay, passive glomerular filtration, active tubular transport. So you can actually go back to the fine anatomy of the kidney tubule, and you can address this very nicely. And that's what we're going to do with diuretics and with other classes. Partial reabsorption or hemodialysis. So it's all factors that can be addressed to you nicely. And this is a decent figure here to show that actually passive reabsorption of lipid-soluble on ionized drug, which has been concentrated to that of the interluminal concentration is greater than that in the prevascular space. And you can see actually from this plot that only the ionized drug can be excreted, and that's very important parameter to keep it in mind. This beautiful proximal tubule loop of Henle distal tubule, you're going to love it when we address diuretics. Okay, so be familiar with that, appreciate those terms. Last but not least, on kinetics of continuous drug input. So keep in mind that you want to achieve homeostasis, steady state concentration of the drug, of the metabolite, of the hormone. That's the essence of life. That's the essence of life. You want to maintain a very well-balanced metabolites, drug and everything, hormones, regulators, signals, cyclic AMP, GS, GI, GQ, all of this proteins. You have to turn them on when they are needed, turn them off when they are not needed. So how you accomplish that? The rate of drug input equal to the rate of the drug output. So that's a simple concept, and when I usually address this material, I actually bring it in a box. What goes into the box equal to what goes out of the box, which is very much the same. So in order to do that, this is what you're looking for here. Okay, so you're looking at essentially the steady state region. So if you infuse a drug at 0 time with a low dose, that's what the kind of relationship that you're going to get in the first plot here. You see low rate of infusion here. If you double the rate, so you're essentially doubling the rate of infusion, so high rate of infusion, so you're achieving steady state at higher level here. Okay, and the bottom line that this is the steady state concentration that you want to achieve. So you can see that a faster rate of infusion does not really change the time needed to achieve the steady state. Does not do that. It's only the steady state concentration which is achieved. But if you really follow this, you see the time to achieve. You follow this as by extrapolating the concentration at half of Vmax here. So if you really draw a straight line here and you intersect it down here, and you do the same with respect to the second one, you will find that the time is very much the same. Okay, let's see that. Half-life is the amount of time to eliminate half of the drug. Okay, so the shorter half-life, so that tells you you need more frequent doses. And hepatic diseases will have an effect on that. Finally, here you see the rate of distribution versus the rate of elimination. They both follow first-order kinetics, and you can determine actually T-half. And it's very clear here how you get it. It's a time which is required for half of the drug to achieve steady state level, or half of the drug to be eliminated. So you can correlate that very nicely. And clinically speaking, you will see actually that you can achieve actually, you can achieve out of this 90% of the steady state concentration will take place after about 3.3 T-half. And that's important to keep it in mind. So I think this slide here shows that information very nicely. You have quantitative aspects here to relate the excretion rate to the plasma concentration, to the clearance, the T-half, and you need to be aware of all of those terms. You need to consider that the total clearance will take in consideration hepatic clearance, renal clearance, pulmonary clearance, and other. Okay, and you have your share on that. The bottom line that you need to master those by heart. There is no way around it. T-half evaluation, you need to know it as well. So T-half 0.693 volume of distribution over a clearance. And finally, this decent plot here, which shows that the half-life of a drug dose does not depend on the size of the administered drug. You see that here. So if you give really a low dose and you get 1/2 of it, so it's the same as if you get a high dose. So if you extrapolate the half-life here and you extrapolate it down, you will find it to be the same. Okay, so that's, and finally, this is just to show you how you achieve a steady state level by giving dose of drug on more frequent, on 2-3 doses, and how you adjust that. And the main significance of this is that you want to achieve and you want to continue on the steady state level that is pronounced on the black curve here. That's what you see in this plot. So multiple IV injection when a drug is given repeatedly at regular intervals, so the plasma concentration increases until a steady state level is reached. Okay, so this is the kind of information you need to get, and with that, we essentially covered everything we want to see on this, and this is the very last one. What it shows here on the blue curve, it shows actually a single fixed dose. So if a drug given orally, that will result in a single peak in plasma concentration, followed by continuous decline in drug level. That's what you see in the blue one. And what you see in the red zigzag curve here is a repeated fixed dose. So when you repeat oral administration of a drug, it will give you this oscillation in plasma concentration that are influenced by the rate of the drug absorption, of course, and the rate of the drug elimination. Those are the two factors that you have to consider day and night. So we completed everything we say. At least we want to make up for the deficient, for the time we lost in the beginning, 5-10 minutes. And what I like to do is, let me see, I already did that, yeah. What I like to do is to shift the gears and address pharmacodynamics, at least to begin with, and then we'll follow this. Pharmacodynamics, what are we interested in? What the drug does to when it gets there, right? Pharmacokinetics, what the body do actually for the drug, how he handles the drug, how he distributes the drug. Okay, so we dealt with this, how you eliminate the drug. But here, what does the drug do when it gets to the biological system? The target here is receptors. And here we, again, there is a need that we address molecular signaling, because that's the only way you can appreciate the sub-specificity that with regard to beta blockers, alpha blockers, alpha 1, alpha 2, muscarinic receptors, nicotinic receptors, and you can name it. The only essence to understand that is to appreciate the fact that drugs act with certain specificity toward certain classes of receptors. So when you talk about beta receptors are predominant in the heart. Okay, so you have to appreciate that and what kind of beta receptors. And alpha receptors, where they stand, and so when you have a class of drugs that bind to alpha receptors. So what kind of effect do you expect to see? That's what you're interested in. So with that said, drug receptor interactions play a major role in that, and that's why I intend to probably address molecular signaling in a little bit more detail, and in detail next time. I did not try, I was reluctant to bring it here, But as you can see, we always ran out of time to address this information. On non-receptor mechanisms, certain drugs, actually, you don't have to bind with the receptor. And you already dealt with that, right? Anti-metabolites, right? You dealt with the statin compounds. You dealt with anti-leukemic agents, like hydrofolate reductase inhibitors, right? Methotrexate and all of that. So there are a wide variety of drugs actually don't have to follow this pattern of non-receptors as a non-receptor bind. Okay. So the receptor interactions or enzyme interactions or non-specific interactions. So what are we dealing with here? You're dealing with actions of enzymes, okay. So you look at the enzyme, you look at the substrate, and then you design actually an analog for this substrate. That's what happened with the statin compounds, okay, and that's what happened with the anti-leukemic agents, like methotrexate, okay. Drug-altered processes catalyzed by those enzymes, and the best way is the monoamine oxidase, my favorite enzyme that I dealt with it actually for many, many, many years. I love this enzyme, monoamine oxidase and CNS system, right? Oxidases 1A and B, and the specificity towards those ones, and also dealing with classes of reversible and irreversible inhibitors, choline esterase inhibitors, and that's what you're going to deal with in cholinergic drugs, right? Agonists, antagonists. So we like to know how you play around with that, and you have a drug that acts on choline esterase that tends to hydrolyze the ester bond and cleave acetyl coenzyme E from choline. Okay, and what's the significance of this? Combining with other chemicals. Some drugs actually you don't need to bother with enzymes, or you don't need to bother with receptors. Antacids, antiseptic effects like alcohol, phenol, chelation therapy. Have you heard of it? Many, actually numerous physicians actually select this route, and they call the chelation therapy. What they do, they inject the patient with some chelating agent like EDTA, right? And they sit in their office, they have easy time, and actually the chemical does the job itself. It's the nature of the chemical that traps those heavy metals, and it's being used effectively in Wilson diseases, copper problems in the brain, and all of that. Changing cell membrane permeability is a factor. So you can appreciate this wide effects of this material. Okay, and we presented this, and we will present it. I'd just like to go over some of the terminology. I'm not going to go over the graphical presentation because that's very important, and probably you can leave this for next time along with the molecular signaling. But the terms here, when you have an agonist, so as the name implies here, you activate. You see, you expect a response, really. So an agonist does this job. Okay, and now keep in mind when we deal with those classes, cholinergic, adrenergic drugs, so those can be classified into agonist versus antagonist. Okay, depends on the need, right? Do you need something to activate, to act in addition to the natural product that you're producing? Okay, so that's a function of agonist. A drug is said to be agonist when it binds and shows an effect. An agonist, as the name implies here, you're blocking actually, or you're inhibiting the natural metabolite or the natural neurotransmitter from binding at its receptor site. So a drug is said to be an antagonist when it binds to a receptor and prevents or blocks the natural compound for the drug have to have an effect on it. So what you expect to see here is that the intrinsic activity is 0. That's what you want, antagonize. Okay. You have to accept the fact also that certain drugs actually work as a team. Okay, so synergism is involved when you have you give two drugs, so you expect to see the effect is higher than the sum of both of them, or in some cases that the combined effect is the sum of their individual effects. So those are all the terms that you need. Partial agonist. Okay, so that's important also to appreciate. So it's going to increase the function of, so it acts as a helper, assister here, and causes partial response. So those are the terms that you need to appreciate. And I think I'm going to stop at this stage because actually I need to spend quite a bit of time in addressing this beautiful plot because it's very important to appreciate that along with the next slide. This is extremely important to have your eyes cleared on this. So I think we do not want to address those today. With that said, I completed my topic for this week, and I hope you have this good opportunity to master this information a little bit more than probably before. And let me now, if I look at the attendees, yeah, we have 15. Yeah, I like actually to see more people attending because we take this in serious consideration, and I love to see more people really coming on board for that. Okay, so that's with respect to the attendee list. I see Dr. Minarsik there, and I see Dr. Jim here. Okay, and any questions, any comments before we leave? Okay, so if not, so you enjoy your great day now, everyone, and see you all next week. Thank you all. Bye-bye.